Okay, in our last video we talked about dihalogenation, the addition of X2. So this is part A to this reaction. We're now going to talk about part B, and this is called halohydrin formation. And this reaction is very similar. It's an alkene addition reaction. We're still adding X2, Br2 or Cl2, but now we've changed our solvent. Our solvent is now going to be water, right? Or our solvent could be some alcohol like methanol. And what that's going to do is water, right, is not just our solvent, it's actually going to be our nucleophile. So in the top example, when we use CCl4, this was our solvent, and that's a non-reactive solvent, okay? It's not nucleophilic, and it doesn't react, which is why we never saw it in the mechanism, okay? But now we're replacing that solvent with a solvent that is reactive, okay? This solvent is reactive, right? And we're going to see that the solvent is actually going to be our nucleophile in this reaction. So as an alkene addition reaction, again, we're going to break the pi bond. In this case, we're going to be adding an X, right, a Br or a Cl, and now an OH, okay? So we do have to follow Markovnikov's rule. The OH, or the OR, is going to go on the carbon that's more substituted. And then we're still going to have anti-addition that we saw for reaction 7A. So if you look at our products here, right, we have two carbons here and here. So we're going to be adding the OH to the Markovnikov position, the bromine to the other side. Same in the bottom example, OH now on the top and the halogen on the bottom. And then anytime we form two stereocenters or more, we have to show the stereochemistry. So in this top example, that carbon is a stereocenter, but that is not, so I don't have to show the stereochemistry. In the bottom example, I've formed two stereocenters, so we have to show that the OH and the chlorine are anti to each other, right? They have a trans relationship. So now let's work through the mechanism so we can see that. And this mechanism is going to be very, very similar to the mechanism in 7A, all right? So let's clean this up a little bit, all right? Work on our mechanism. The first steps are going to be the same as we saw in 7A. I'll take my halogen, right? Each chlorine has 3 lone pairs. The bond in between is weak. So our pi bond is going to attack one of the chlorines and then break the chlorine-chlorine bond. Okay, so we will attack that. This is the same exact first step we saw in 7A. We're going to add our chlorine to one side, which means we have a carbocation on the opposite side. Remember what we saw before, because the chlorine has lone pairs, it can stabilize this positive charge by actually forming a bond to it. So the chlorine can donate one of its electron pairs, right, to form that bond. It therefore only has 2 lone pairs. Now it only has 6 electrons. It's missing 1 from the 7 that it wants, and it has a positive charge, right? Or the chlorine can reside on the other carbon at the bottom, or sorry, the chlorine at the top. Okay, so these are the intermediates that we form, exact same first step in 7A. So again, while we form our Cl minus in this first step, what we have to recognize is that we now have solvent, and we have a lot of solvent, okay? So our solvent is going to be in a huge excess. So when we talk about which nucleophile is likely to react, we have so many more solvent molecules that that's going to act as our nucleophile. Okay, so we're now going to take the lone pair on the oxygen, and that is going to attack that carbon, right? Or you can kind of say we attack this carbon and break that chlorine-chlorine bond. So that is, again, another attack step. We have to remember in this step, right, because this chlorine is blocking one face, our nucleophile is going to come in on the opposite side. So this is where we establish our anti-relationship. So here's my new bond to the oxygen. Our O had 2 bonds to H and 2 lone pairs. One of the lone pairs has become our new bond. So that oxygen is still connected to 2 H's and now only 1 lone pair. That oxygen now only has 5 valence electrons, so the O has a plus, right? And our chlorine here is still there, right? And that chlorine is now going to be opposite of our new nucleophile, right? So because I drew this as a dash and back, then that chlorine has to be a wedge, all right? Because our final product, right, we want it to be neutral and stable, there's one additional step here, right? So what we have to do to get our final product is we have to deprotonate one of these H's. And again, to do this, I could take Cl- that we formed in the first step, or I can even use water. And I'm going to take one of these lone pairs, either the Cl or that lone pair, and I'm going to form a new bond to the H and break the hydrogen-oxygen bond, which becomes a lone pair on the O. So let me kind of draw the product over here. So here's our deprotonation step, right? So what we can do here is we see that we still have our methyl pointing up. We now have our OH back. Again, we've lost one of the H's, so we've got a new lone pair instead, and then we still have our chlorine here. So we've maintained this anti or trans relationship, all right? And again here, when I did my initial attack, right, I had the OH come back, but you have to remember half the time it's going in the other direction, right? So when we form this, we're also forming the other enantiomer where our methyl is back, our OH is towards us, and then our chlorine is back, right? We have a racemic mixture of these two, right? And for us, we just have to draw one or the other. I don't really need to draw both. So it's the same concept as 7a where you have anti-addition, but because our nucleophile is different, we're now going to be adding kind of an OH, and that goes to the Markovnikov position, all right? Let me just show you one other example, right? If I draw something like this, and I treat this with Br2 in methanol. Methanol is a reactive solvent, so instead of water attacking, the methanol is going to attack. So what's the product we're going to get out? Because we're forming 2 new stereocenters, we have to draw the dashes and wedges, and instead of having an OH, right, we're going to have an OMe, right? Because in this step here, you deprotonate. You take one of the H's, and there's only one H to take. So you're left with an OMe, right? And then we still have to add our bromine, keeping this anti or trans relationship. And again, this final product here is racemic, right? Which means you can have the OMe back and the bromine towards you, or it could be vice versa. You could have the OMe coming towards you as a wedge and the bromine back. You can draw either of those examples. All right, so that's halohydrin formation.